Hello, my name is Stanford Gibson. I'm the Sediment Transport Specialist at the Hydrologic Engineering Center and in charge of the sediment transport features in HEC-RAS. This is the third video in a series that walks you through how to create a semicircular flume in HEC-RAS and compute both clear water and mud flow simulations in version 5.1. The first two videos just really walked you through setting up the terrain. First half of this video will show you how to set up a standard flow simulation in HEC-RAS. If you're primarily interested in the new Non-Newtonian features, you can jump ahead to about the 10-minute mark. The model we're building is simulating an actual flume experiment. This flume experiment was conducted by Parsons et al., Parsons, Whipple, and Simoni, and was published in the Journal of Geology in 2001. They conducted about 30 different flume studies in these 10 to 15 centimeter half pipes with at least 7 different materials at really high concentrations, volumetric concentrations above 65%. And so they make a really good test case. We simulated 10 of these, but in this video we're just simulating one that uses a relatively fine material. So our last video left off with a terrain that we built from our 1D cross-section and then created our 2D mesh. Now we don't need any of that 1D infrastructure anymore, but I'd love to keep it. So let's save this geometry data as and just call this the 2D terrain of experiment 1A. And then we can go in and get rid of that 1D infrastructure. We can go to Edit, Delete Reaches, and select the reach, and yes, we want to get rid of it, and that will also take the cross sections with it. So now we're just left with the 2D mesh and the terrain underneath it and are ready to go. The first thing that we're going to need are boundary conditions, and the boundary conditions we're going to define right in this geometry editor. And so we come up here to storage area, 2D area, BC lines, which are boundary condition lines, and that's going to allow us to draw some break lines. I'm right clicking here in order to zoom in, and I'm going to create a boundary line from here to here to cover all of those upstream cells. And I'm going to call that upstream US. Now I wasn't super careful about where I clicked those nodes because I'm going to go in and georeference them. All right, and you can see that RAS created a boundary condition line at the upstream cross section. So now I'll zoom to the full plot and zoom in to the downstream boundary, and I'll do the same there. And I'll call that downstream. Okay, but now I want to make sure that those are actually exactly where I want them. So I'm going to go to GIS Tools, 2D Flow and Boundary Condition, Data. And my upstream boundary is basically just going to be those two left nodes of the polygon I used for the 2D area. And then the downstream boundary will just be those two nodes. And so then it's exactly where it needs to be. It would still work if you didn't snap those on. The RAS is kind of geospatially sophisticated enough that that generally works, but I just like to be precise. Okay, so then we save it. And now what we're going to do is create an unsteady flow file to generate our boundary conditions. Non-Newtonian is all in unsteady flow, whether you do it in 1D or 2D. And to get an unsteady flow file, you either have to go to Edit, Unsteady Flow Data, or push the flow data that looks like a hydrograph. And you can see that this populates automatically with an upstream boundary condition and a downstream boundary condition. The downstream boundary condition is going to be easy. This is going to be normal depth because we actually know the slope of this pipe, and we're going to define that. Now, the non-Newtonian effects are going to actually affect the friction slope, and so that's going to be built into that solution, but for now we'll just go ahead and put in the slope of the flume. Next, we're going to define the upstream boundary condition. So we'll click on that upstream node, and we'll press Flow Hydrograph, and we'll get a flow time series editor. Now the flows in this flume are very small, and in SI the flows required in the upstream boundary condition are in meters cubed per second. Experiment 1A had a flow of 1.89 liters per second, which is 0.00189 meters cubed per second. And it turns out that is beyond the rounding tolerance of RAS. And so we're going to kind of trick RAS here. We're going to put in the flow of 1.89 liters per second, even though it's in the wrong units. And then to populate the rest of the time series, I usually just scroll down to the end of the time series and type it again, 1.89, and then press interpolate missing values to get the full time series. But now we're in the wrong units. So what I'm going to do is I'm going to come to the multiplier field here and put in a multiplier of 0.001, which will convert our liters per second to meters cubed per second and give us the flows we want. Then the last thing we need is we actually need an energy slope that RAS will use to distribute flows across that upstream boundary condition. Here we'll just use the slope of the flume, which is the same slope we've used for the other boundary condition. And I'll turn on tailwater check. So now I have a water flow boundary condition. I'll go to save as, and we'll call it water flow to distinguish it from the non-Newtonian flow later. And we're ready to do a water simulation. So we'll come and press the running man, running up the hydrograph, or go to run unsteady flow analysis. And that will open our plan file. I'm going to go to File, Save Plan As, and call it Water Simulation. We'll call this H2O. And we're going to turn on the preprocessor and the unsteady flow simulation, and then we need a time window. I don't know exactly when these experiments were done, but Parsons, Whipple, and Simoni had their manuscript accepted to the Journal of Geology on the 5th of March 2001, so that's as good a date as any. And just a note to international users, this is a US date, and your computer needs to be in a mode where it can recognize US dates. That's one of the most common errors that international users run into. And let's start at time 0, and we'll run it for 1 minute. Now, as for the time step, this is a very small cell and a very steep slope. So I'm sure you can imagine we're going to use the smallest possible time step, but it turns out that's not actually small enough. And so what we're going to do is we're going to ask RAS to actually subdivide the cell based on the Courant condition. So to subdivide the time step, you can press the ellipses here. These are just computational options, so you can go there as well. And we're going to click on Advanced Time Step Control. Here we'll say, hey, adjust the time step based on the Courant condition, and let's keep the maximum Courant condition less than 1. A minimum of 0.2 will work. And then we'll change these to 4 and 6. And what that'll do is it'll monitor the simulation to make sure that the Courant condition doesn't exceed 1, and it will subdivide the time step, having it up to 6 times in order to achieve a time step that gives you the appropriate Courant condition. All right, and then while we're in these computation options and tolerances, there are actually a few other things that we need to do. So if we go to General, again, our water surface calculation tolerances are set to prototype scale. We want to be much smaller than that. And so we'll say 0.006 for both of those. And then in our 2D options, we're going to want to go with the shallow water flow equations. We're going to want to set these tolerances smaller as well. And then we're going to put in some basic mixing coefficients, 0.3 for longitudinal, 0.1 for transverse, and 0.05 for Smagorinsky. These were selected kind of a priori. These are very standard mixing coefficients. And we'll say OK. The last thing we want to do is we want to set our output to 1 second, and let's set these to 1 minute. And we're ready to run. So through the magic of time lapse, we're going to skip some of the runtime here, but I will point out that this Courant condition time control does subdivide the time step to 0.003 seconds, which is why a relatively small flume with 4,000 cells is going to take a couple of minutes, but it's appropriate for the level of simulation we're doing. And we're done. Took a couple minutes, and now we can go and we'll go to RAS Mapper to view those results. You can see that the results tab now has the plus sign, so you can expand it out. And so we can go and look at the velocity results, and we can animate them, or we can step through them. And let's just zoom in a little bit here to see them. And you can see we've got kind of maximum velocities in the like 1.5 range. So if we come in here and say layer properties, let's set our max at 1.5 instead of 15. Create. Okay. We now plot velocities on a reasonable scale and can watch it flow down the flow. All right, so we have a standard RAS flow simulation at this point, and to this point we haven't done anything you couldn't do in 5.0.7. What's new in 5.1 is the non-Newtonian mud and debris flow simulations. And if you look at the image of these actual simulations, these are very high concentration materials. The particular material we're dealing with here has a lot of fines in it, and so this is a mud flow simulation. And so we are going to now add some mud and debris flow parameters to simulate this as a Bingham plastic. So the mud and debris data are in the unsteady flow editor. So what I'm going to do is I'm going to save this as a new unsteady flow file that I'm going to call Bingham. I'm going to leave all the flow boundary conditions the same. What I'm going to change is I'm going to go to options, and down here we have this new option called Non-Newtonian parameters, and that opens this Non-Newtonian parameter editor. Now if you click here, you'll see that we actually go into several of these in the paper. In the paper we simulate these experiments with turbulent dispersive and Herschel-Bulkley, and the RAS documentation will go into many of the other ones. This is all reaching to a non-Newtonian library called DebrisLib, which was developed jointly between HEC and ERDIC Coastal Hydraulics Lab, led by Ian Floyd. And the idea is this library can be accessed by multiple software. In fact, several software, including RAS and ADH, are accessing this right now. But what we're going to do is we're going to really just choose the simplest model. We're going to choose the Bingham plastic model. Now the fundamental properties of a Newtonian flow are that in the stress-strain relationship, it's linear and it has a zero intercept. There are a number of very complicated rheological models you could use to simulate non-Newtonian flow, but the simplest is just a Bingham plastic. And a Bingham plastic first has a non-zero intercept, which means that you can apply a certain amount of stress to it before it moves, and so it has what we call yield strength. And then the slope of the stress-strain relationship, once it does move, is higher than a Newtonian fluid, because the slope of the stress-strain relationship is just the viscosity of the material, and the sediment-laden viscosity of a thick mud like this is quite a bit higher than water. And so what we're going to need to define is the yield strength and the viscosity. Now these are actually pretty difficult to come up with, and so generally what we do is we use the O'Brien equations. O'Brien has actually developed a couple of power law equations that will compute these parameters based on some measured coefficients for different soil types. And we've used some of these in studies and they've performed relatively well. But in this case, the experimental team actually measured and fit parameters to these simulations. And so we're going to use the fit parameters that they selected. And so in both cases, we'll say we're going to select a user yield, and we're going to set a user-defined sediment-laden viscosity. And so the yield that they fit was 98, and the viscosity was 1.92. Now this is all in SI, so we're in Pascal units here. And then the two other pieces of information you're going to need is a representative grain size. The representative grain size is 0.2 millimeters, but that actually doesn't get used in the Bingham plastic. What does get used is the volumetric concentration. And the volumetric concentration of this material is 69.2%, which is a lot of sediment. Now, there are lots of different ways to specify and report concentration. And at very low concentrations, the kinds we encounter in alluvial transport, a lot of these ways of reporting concentration, the differences are trivial. But once you get up into these sorts of concentrations, these mud flows and debris flows, the difference between volumetric concentration and concentration by mass and parts per million and milligrams per liter can be dramatic. And it can also be pretty confusing to parse them, so we've added a concentration conversion calculator where you can go in and select the units that you're going to define your concentration in, and it will convert that into the other sorts of concentrations or water contents that you would be interested in reporting. So that's it. We're going to say OK. We're going to go File, Save. And we'll open the plan file, and we'll save this as Bingham. And everything else will stay the same. And so we'll simulate that. And then that simulation completes. We come back to Mapper, and now we've got a second simulation here called Bingham. And you can see that this simulation has a different shape, different velocity. If we come here and set our velocity scale to the same one that we did with the water flow, press Create. You can see that we're traveling a lot slower than the hydraulic solution. You can actually turn them both on at the same time. And let's actually move the Bingham simulation up. So you can see the different size and shape. The Bingham simulation actually looks more like the Parsons simulation. And if we get a time series plot of the velocities, you can see that the Bingham velocity is about a third of the clear water flow. Now, is that correct? Actually, it is. The simulation turns out to match the velocities quite well. The Bingham model actually does a relatively nice job, has a root mean square error of about 0.21 for all 10 simulations, but the paper goes more into all of that. And so that's a very basic introduction to non-Newtonian modeling in HC RAS, and provides you with a data set that you can build from scratch in order to start playing around with it. The mud and debris flow capabilities are only in RAS 5.1. We'll be pushing a beta version out of 5.1 in the next couple of months. If you would like to alpha test the mud and debris flow capabilities, if you have a data set that you're actively working on or a data set that you've simulated with a different model, I am showing an email address on the screen, and you can send me an email, and when we're ready to push out an alpha version, I may reach out. So that concludes the three-part series that has walked you through the process of modeling clear water and non-Newtonian flow in a semicircular flume starting from scratch. This work and video was funded by the Flood and Coastal Flood Risk Management R&D program of the U.S. Army Corps of Engineers, and in particular of the Post-Wildfire Flood Risk Management Work Unit in that program. That work unit is headed by Ian Floyd, who's a co-author on this paper, along with Ronnie Heath and Alex Sanchez. I may do another video just summarizing the results of the paper. These videos are essentially a digital methods and material to a paper that we'll submit shortly after they're published. And once the paper goes through the review process and is accepted at a journal, we will clean these videos up and post them in an official capacity. Until then, feel free to go ahead and make comments on the video, and I will try to make improvements for the final publication.